Thank you for the introduction, and thank you for the organizers to invite me and give me a chance to presentation. My today's talk is complex valued nonlinear PDE, especially so far as I know, Laplacian equation have been studied only in real valued case, but currently I'm working on some AI project, and in there they somehow extended the linear equation to the complex valued for some numerical result. So I'd like to somehow extend it to the nonlinear equation. And easiest way is for the elliptic Laplacian equation. So here, we are considering this Laplacian equation, and I'm interested in extending the first term and this coefficient part to the complex valued. And so if we extend it to the complex valued, then solution must be in complex valued. So in this situation, let me first introduce the setting, like how we extend the integration by part, or the weak formulation, or the ellipticity over the coefficient. So we have to know there is really a solution for uniqueness and existence. Regularity properties are these are my interest. And complex space, I mean, so if we take some function in here, then there will be a real part and imaginary part. So basically, it's the vectorial real valued four-level space. They will be equivalent. Okay. So for the first setting, to define the integration by part, so integration by parts will be, so energy estimate will take place by using the complex conjugate inner product. So for any complex number, so let me denote its complex conjugate in this way, so taking bar. And this is the vectorial case. Whenever there is some n component, for this vectorial case, let me denote the complex conjugate inner product by in this way. So there each component are multiplied by using complex conjugate. This way. So this is the natural extension of a complex conjugate product. Then naturally the norm will be defined in inner product. Okay, so for the equation, we will assume coefficient is just bounded, and first term is in some P prime. The weak solution is in W1P space. And so we define the weak formulation by, for any test function in here, we take complex conjugate inner product in this way, and the first term in this way. So here, there's a one thing remark that the coefficient function is not inside of the complex inner product. So this is somehow related to the Lax-Milgram theorem when linear case. The one other reason is that if there is a free complex number in some is in here, then the calculation becomes too messy, and I think it's very hard to get some coercivity or some other properties. So next, let me explain the coefficient function. For the coefficient function, let me write real part as AR and imaginary part as AI. And trivially, we can write and decompose in this way with I standard imaginary number. For the ellipticity, we assume that there is some constant such that AR, the real part minus absolute value of imaginary part is somehow strictly bigger than U, and they are bounded by some uniform constant. Okay, so in the coefficient, the real part, it must be real positive valued, but we are allowed to AI to take negative values. So for the coercivity, so this will be something like coercivity, because this is a complex number. So the coercivity always coercivity is only in the real part of this value. The operator again is bounded because the coefficient is bounded, and this is just the p-Laplace operator. For the proof of existence and the uniqueness, we need some kind of monotonicity for the p-Laplace operator. And for this, we will impose one more condition. So for this, introduce that for any factorial complex number, there will be real part and imaginary part. So let me write this for denoting this way. So if this hat is like so this is the thing we need for the monotonicity, and when we prove the energy estimate by uniqueness, when we prove uniqueness by energy estimate, we need this kind of this estimate. But using this notation, we can write in this way. So in the real part, this is a real part, the operator. This is like just like the factorial case of Laplace operator. This part is a little bit out of control. And so if we use this kind of notation, then the norm is always they are the same. So, like the coercivity, monotonicity also only in the real part of the operator. So if we take the real part of the operator, then real part of A and the real part of this, and imaginary part of this, and imaginary part of this operator part will be the real part of for calculation. And in here, we can apply the structural condition of a p-Laplace operator. This is the condition of monotonicity of a p-Laplace operator. For the second term in here, we just take absolute value of in this way, we have C, there will be some constant only depending on P, C1 AR, and C2 absolute value of imaginary part of A. So if we further assume this kind of condition, then it says like it is the monotone property of a real part of the operator. So we have uniqueness. So suppose A the coefficient satisfy previous ellipticity conditions. Suppose F is from first, F is in the first term and G is boundary data from domain. Then if we try to prove the uniqueness, then just we consider the difference of the equation and just add, take u minus w as the test function. So this is exactly the because the first terms are 0 in the difference of the equation, so we have this energy estimate. We take the real part of this one, left and right hand side, and using the monotonicity property of the real part, then this becomes 0. Means u is equivalent to the existence also very similar to the real valued theory. Again with the same condition. Suppose we would like to show the existence of the weak solution. So if we somehow adopt the monotone operator theory, then based on the fixed point theorem, then this can be also be proved. So this is the lemma that used for the monotone operator theory for the real valued case, but originally this is like Rm to Rm. This is the real, but in case this is the mapping from the real complex space to the self. Then if the condition is only true for the real part, then the same conclusion holds. Okay? So the proof is analogous. So the W01P space is equivalent to the this vectorial setting. So the function space is separable. So from the finite space, we apply the this fixed point theorem to this space, and if we use the monotone operator theory based on the property of monotonicity of operator, and we can also prove the Minty-Browder method and the solution. We can prove the existence of the solution. Finally, regularity property. So let's first think about the this kind of homogeneous equation with a constant coefficient and the first term. And there is a observation that gradient is locally held continuous. So to prove that, for given solution, we define the vectorial function W in this way. So this is the real part of V and imaginary part of V. This is a vectorial map. And now I claim W is the weak solution of this equation. So this is a real valued solution of Laplacian equation. To prove that, let's take test function in this space, and from this test function, we could make complex function. And originally, W is the V is a solution of homogeneous equation, so this is trivial. And in here, we don't have any some coefficient or nothing. So we remember then the real part is it's just the inner product of these functions in order. The imaginary part there, it is messy, but if we just take the real value of this one, then gradient of V is equivalent to the gradient of W because they are the same. And so we can replace here by gradient W, and here is just first component of gradient W and second component of gradient W. So this proves this claim. So following the Ullenberg's Acta paper, then gradient W is locally Holder continuous. Then so they have same component. So gradient V has locally Holder continuous. Because we have energy estimate using the monotonicity, and we have the gradient and the regularity for the homogeneous equation with the constant coefficient. So we can also apply the powder estimate. Already there are many experts here, so I'm not going to say any details. But we can follow exact the same argument in the real valued theory, and we could conclude that if coefficients are additionally held continuous and source term are held continuous, then solution of weak solution is locally held continuous. Okay, so the linear case is first studied by Cohen, DeVore, and Schwab in 2011. But they are interested in some kind of parametric problem for the numerical result. Matthias and I have extended to the Laplacian case and will be uploaded in archive. Yeah.